all digital reconfigurable SRAM-based compute in memory macro for tinyML devices. So Runxi Wang is actually a IEEE and ACM student member, a current senior undergraduate student, and an incoming Ph.D. candidate student from University of Michigan-Shanghai Jiao Tong University, Joint Institute in China. She's a member of ICAS lab led by Professor Xinfei Gao, and her research interest is on computer architecture, computer in-memory, and reconfigurable architecture. She received Women in Technology Award in 2021 AMD Xilinx Adaptive Computing Challenge. Over to you, Runxi, for the session. Thank you.
Okay, thank you for the introduction, and thank you for everyone to attend my talk. And I'm Runxi Wang, a senior student from University of Michigan, Shanghai Jiao Tong University Joint Institute. And the topic of today's presentation is an all-digital reconfigurable SRAM-based compute and memory macro for tiny machine learning devices. So here is the outline of my presentation. I will firstly go through the motivations of my project, and then I will cover two main parts in our design. And also I will give the evaluation results for our design. And finally, I will summarize our work and give the plan for our next step. So we know that the artificial intelligence is still in the booming stage. We can see the in the expected future, the market size of AI can increase exponentially. And in our lives, AI is actually everywhere. We may use it in the facial recognition system or applications, and also in the autonomous driving. And apart from this, we do see AI getting involved in the financial system or the data security field. But in this project, we are focusing on the tiny machine learning on the edge. So I have listed three characteristics about the tiny machine learning on the edge. The first thing here is that so we are computing on the edge. So we capture data using the edge device, and so we will fed the data directly to the edge AI model, and then we can get our expected results. So compare with the conventional cloud computing, the edge computing can save much time and energy because we can eliminate the data transfer cost for a server or other things. But even though edge computing can do this advantage for us, it does have some limitations. The example I raise here is about the limited hardware resources and power supply, because for edge device, most of the time we want to make it portable, to make it smaller. In this case, we have very limited chip size or the hardware size. And yeah, so compared with the server, we do not have that much computing capability because we most of the time it is hard for us to equip a GPU or something else to the edge device. And when we are considering attach a AI model to the edge device, we need to consider the model scale, whether it matches the computing capability we have equipped on the edge. But even though under such a constraint, nowadays, our AI algorithms are becoming more complex and more diverse nowadays. For example, we do have more layers or more weights in the AI models because we want to have better performance or better accuracy for the model. And in such a condition, we need to find a way to both store and compute the data efficiently. Yeah, that's the first motivation. So we are thinking about to find a straightforward solution to reduce the energy consumption and the latency, and still we can maintain the performance as expected. So here I have a short introduction to the computer memory. In the left-hand side part, we can see a conventional architecture such as the von Neumann architecture. We've got the we have two separate parts, which is the computing unit part and the data storage part in the conventional architecture. So if you want to perform a very complex algorithms like the convolutions, we need to firstly fetch the data and do some repeated computation in this computing unit. And we will generate many intermediate results, and maybe they need to be sent back to the data storage. So in the process, we will have very frequent data transfer, and this will induce a large amount of energy consumption and also increase the latency. So the solution we want to put here is the computing memory, which means we put partial computation logic into the data storage part. So the diagram here is shown an example about the computer memory that is combined into the cache, but we, of course, we can put the computation logic into DRAM or other memory technology. And according to some previous works, we can put the computing logic into the cell of this SRAM array, which means infuse the computation logic into each bit of this array, or we can stacking the computation logic surrounding this array, which means the peripherals here. And by utilizing such a approach, we can have lower energy consumption and lower latency because we reduce the data transfer rate. And lastly, but also the most importantly, we can see the structure of this computing memory array. It is physically useful for NN calculations, like the vector or matrix-based calculations. If we can do it just in this location, we will save much more energy or the time. And for the third motivation here, it is more about the performance and the flexibility. So to execute a larger range programs in our accelerator or in our edge device, we can use a general purpose accelerator. In this case, we will have less cost because you can run almost any programs in it, but we will have less performance for each of the algorithms we want to support. And in this case, we may think about to use a fully customized accelerator, but here we know that since it is fully customized, it will have less flexibility, and also we will have greater performance because it is fully customized and will be well optimized. But the cost, finally, the total cost for the whole range of algorithms will be very large. So here we want to strike a balance between these three factors. So we are thinking about to use a reconfigurable accelerator. And thinking about some previous works, so according to our preliminary research, we have seen that the previous works, the previous computing memory works, they mainly focus on single hardware level computing memory design. So here I use this pyramid symbol to show that maybe they just focus on proposing a new computing cell, or they just propose a new peripheral circuit, or just focus on system level. And recent works, mostly in this 2 to 3 years, we also see some works that be aware about the reconfigurability for the computing memory. But we do see that their works have a little bit small reconfigurable scope, which means, for example, they just focus on reconfigurable calculation precision. But we want to improve the reconfigurability to our final design because we want to strike a better balance between the performance, the design cost, and also the number of supported functions for the edge AI scenarios. And so here we claim that we want to do a cross-hardware level reconfigurability in our design. So let's go to our design part. So here is a diagram for our design. And in the orange rectangle here, you can see the word line separated 60 SRAM cell. And compare with the conventional 60 SRAM cell, the only difference here is the separated word line, which means each of this access transistor was are controlled by different word lines. And something special here is in the bottom part of this diagram, we can see a colony shared computing logic, which means these computing logic, these 4 transistors are shared by this whole column. And it can perform 3 different Boolean operations by configuring the word lines, read word lines here. So for the computing logic in the left-hand side part, which is connected to the bit line, we can configure the input data or the calculation mode configuration data from the read word lines here. And for the right-hand side part, we can configure these 2 wires. And so the result will be generated from the read bit lines here. And the detailed configuration can be shown, can be read from this table. So here the features is that we support 3 different Boolean operations with low area overheads. And for the reason why we have low area overheads here, because we know that for some previous works, they have their computing logic combined in each of the cell, and this will increase the area overheads a lot. So in this work, we utilize an idea to share this computing logic in the whole column, and so that you can see for a whole column, there is only 4 transistors overheads, and it can be amortized for each of the bits in this column. So the finally area overheads for each of the bit will be relatively small. And for the second design part, here is an overview of it. We call it a reconfigurable computing peripherals. So as I have marked here, it is a peripherals that mainly for addition, and it will be work with the array or the column I have mentioned above. And yeah, so the calculation process will compose of 2 parts, which the first part was done by the blue part, the columnly shared computing logic, and the second stage will be done by this computing peripherals. And I will give a short demo about how to do the bit serial addition. So here we want to calculate a addition. We want to calculate the addition between an input data and the data stored in this array. So we have the data arranged as from the least significant bit to the most significant bit. And the input will be also entered bit by bit from outside. And so firstly, we will read 2 adjacent bits from 2 of the bit lines here. And then they will be fed into the columnly shared computing logic here. And at the same time, we will have the input bits, 2 adjacent input bits fed from the external part. And they will be calculated in this Boolean operation part. So after we have generated the XOR bit and AND bit from the columnly shared computing logic, the 2 bits will be fed into the computing peripherals. So the rest of the computation logic will be done in this part. And we can see that the AND logic, the AND bit here will be used to calculate the carry bit. And the XOR bit will be used to calculate the sum bit. So if you want to get the result for the addition, it will be generated from this port, bit by bit, from the least significant bit to the most significant bit. Okay. And so let me introduce some of the features in this part. In this design, we support concurrent reading. We can see that we make use of the conventional 2 bit lines and read 2 adjacent bits concurrently. And since we are connecting to colony shared computing logic to each of the bit lines. So we can have concurrent Boolean operations performed by these two parts. And we also introducing the concept of pipeline to the bit serial addition algorithm. So we separate the addition process into two stages so that we can finally increase the working frequency of the clock so that to decrease the latency for the total process. And so to summarize here, we will have lower latency, so which I have mentioned both. And even though we just shown a addition process here, but we can see that the addition process or the accumulating process will be beneficial for the calculation of MAC, which is a critical part in the neural networks algorithms. And you may say that we have many registers or gates here in the peripherals. This may increase the overheads for the design. Yeah, because here the registers and the gates can be reused to combine to the other form of the circuits, and we can do some other arithmetic operations just by reusing this part. And we are still exploring to use this part to do a maximum finding algorithm. Yes. And for the evaluation part, here is our experimental setup. We use a simulation-based evaluations. And tools we used are Genus, which is for synthesis, and Virtuoso, which is for spectral simulation. And for the technology node we used, that is the TSMC 28 nanometers. And the metrics we are caring about is for the post-synthesis area and also for the working frequency. And we also care about the latency and the energy consumption for the operation we support. So the first part of our evaluation is actually for the Boolean operations. We have introduced both. The waveform is our simulation result, and the green part shows the bits stored in this orange cell. And yeah, you can see that we actually stored M1 here. And the two blue waveforms shows the input and configuration data we have put into these two wires. And the results was generated from the read bit lines, as I have mentioned both. And so the red waveforms just correspond to the result generated here. And if we have more time, we can match, or we can look up the table for the configuration part so that we can see that this part is functionally correct. And for the computing peripherals, I shown both. And we used a simple test case to show the bit serial addition process. The example here is 2 plus 9, or 2 plus 11. And the result we generated from the sum port, which is here, is 1001, which is correct. And the working frequency for this whole process can reach up to 3 gigahertz. And the latency for the 4-bit addition is within 4 cycles. And the energy consumption for this process is about 0.041 picojoule. And we have our cell area after synthesis for the computing peripherals for about 12 square micrometers. So about the comparison part, so compare with the previous works, we have, for the cell level, we have more or the same Boolean operations supported with less area overheads. Because compared with some previous design like the 80 or 10T or 12T, we may support the same number of Boolean operations like the AND or XOR. But since we share the computing transistors, we can to somehow reduce the area overheads here. And there's something new, that is we use the concurrent reading and computing because we are using a fully digital design. And for the peripheral level part, something new here is that we introducing the pipeline concept to the bit serial addition scheme, because we know that we do have another addition scheme called bit parallel addition, and it will increase the latency. It will reduce the latency compared with this bit serial addition. But the bit serial addition advantages have the advantage of increase the throughput. So because we also care about the throughput as the metrics, and we want to reduce the latency caused by that. So we are trying to pipeline the whole process to see if we can reduce the latency, whether we can reduce the latency. Yeah, and there's other thing that I have that I also mentioned above, that is we have reusable components for the peripherals, so that in addition to this addition scheme supported in this peripherals, we can just add some gates or a max to do some other arithmetic calculations based on the computing peripherals proposed above, so that there is more flexibility with less area overheads. And this is a more detailed table compared with previous works, and we actually targeted at more flexibility compared with previous works. Yes. So to summarize my work, and in this project, we have reached a multi-logic SRAM cell, and we are also working on the reconfigurable computing peripherals. And compared with previous works, we have more flexibility with smaller area or some other overheads. So for the next step, we will move on to the architectural and system level design. So this part, I put it into two subsections. The first part is about the design. We want to explore more arithmetic operations to be supported by the peripherals I have proposed above. Yeah, so that to increase the flexibility. And we will treat the existing design as the building blocks to make a scalable architecture. So our reconfigurability also covers the scope for the precision, the kernel size, the model size for the neural networks model. And yeah, and the third thing here is that we also want to dig out something about the data flow scheme, and this is for the architectural level. We want to think about how to load the weight or load the input to our computing memory macro more efficiently, so that we can also reduce the area overheads and also increase the throughput. And the second part is about the testing. You can see that I have mentioned that our evaluations part are based on the simulation, but we do want to do some more detailed post-layout simulations, which will give us more realistic results. And the second point here is that, yeah, since we are exploring a cross-layer reconfigurability, and there do have some overheads due to our reconfigurability. So we want to model this flexibility and overheads quantitatively better. Yes. And this is our reference. And I think that's all for my presentation. Thank you very much.
Thank you so much, Runxi, for the deep dive into the design and the test. It's very insightful.
Good. Once again, we want to thank our sponsors, Tiny Edge Impulse, one of the leading what's called platforms for EdgeML and using tinyML applications. Our executive sponsors, Qualcomm, who have advanced AI research to making efficient AI ubiquitous, both hardware and software. Syntiet, accelerating your edge compute. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. Kilkatech, global IoT solutions. Renesas, basically big ideas for every space. The Sony Semiconductor Solutions Corporation. Gold sponsors, Analog Devices. ARM, who also have their own talks, so please feel free to sponsor them and jump onto their line as well. FortiHub, making over-the-air firmware and model updates simple and accessible. That's probably one of the key things moving forward. So have a look at FortiHub. Microsoft for their edge capabilities and technologies, including all their, I guess, Azure services to support tinyML. NXP, together accelerating breakthroughs that advance our world, a great hardware provider. SenseML analytics toolkit suite to be able to do your AutoML capabilities. STM microelectronics to provide extensive solutions to make machine learning easy. Synaptics, engineering exceptional experiences. And then a list of silver sponsors, including AIZip, Aeon Devices, EMSA, Greenwave Technologies, Gravity Inc., IBM, Imagimob, Etermis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK and Vincent. So thank you once again for attending. I hope to see you tomorrow online to listen to some of those interesting presentations. And thanks to everyone. See you soon.